This video is on the objective compute the value of the test statistic, or the t-value or t-score, and degrees of freedom for a hypothesis test for one mean with an unknown population standard deviation. Okay, so we're differing a little bit from previous videos where we had a known population standard deviation, and that was a z-test, or you found a z-score for your test statistic. When the population standard deviation is unknown, when sigma is unknown, then you're going to be performing what's called a t-test. Your test statistic will be a t-score, right, from that student's t-distribution with so many degrees of freedom. And this is number 1. Alright, so the first video on a question related to this objective from your Newton Alta homework. And let's take a look at it. Okay. So again, if you're unfamiliar with the topic, you want to see some more about it, click on More Instruction and take a look at their videos, their notes, their examples, and hopefully those help you out. Alright, so if a hypothesis test were to be performed, in which of the following contexts would a t-test be appropriate? I would use a t-test. Okay, so this one's not even asking us about, finding the test statistic or degrees of freedom for the student's t-distribution that we're going to need just yet. It's just asking us, in which of these scenarios would we be performing a t-test? Alright, so first off, I'll read through them and explain what's good about them, what's bad about them, if anything. If we're trying to say we want to perform this t-test. So number 1, a simple random sample, which is what you want. Alright, and I'll start writing out conditions for a t-test on a piece of paper. Alright, if we're performing a t-test instead of a z-test, right, like we had been performing, well, 1, sigma, right, sigma is unknown. You do not know the population standard deviation. And then that thing that was mentioned in the first option there is what you want as well, and this is the case for most hypothesis testing you do. The sample is a simple random sample. And it's probably been a while since you saw different kinds of sampling methods. Cluster sampling, stratified sampling. But remember, a simple random sample means that the sample was taken in such a way that every possible group of that size had an equally likely chance of being selected. Okay, so we got that down. So a simple random sample of 19 students is taken from a school of 1,188 students, so as your population, with an approximately normally distributed heights, right? So the population's approximately normal. When that's the case, it doesn't matter what your size is. Now, if the population is not normal, then you have to take a sample size large enough for the central limit theorem to apply. Remember the central limit theorem? So if population is approximately normal, or just normally distributed, then sample size doesn't matter. Alright, sample size won't matter. The distribution of sample means for that size will be this student's t distribution with, so many degrees of freedom. Again, that's because sigma is unknown by the central limit theorem. The distribution of the sample means for samples of whatever size you took, in this case it's 19, will be one of these student's t distributions. Now for other populations, with distributions that are not normal, the sample size needs to be pretty large, relatively large, usually greater than or equal to 30, in order for the central limit theorem to hold, in order for the distribution of the sample means to be that t distribution with so many degrees of freedom. Okay, so what kind of population you're pulling from matters, and also if you have a certain kind of population distribution, your sample size will matter. But if the population is already normal or approximately normally distributed, then the sample size won't matter. The central limit theorem will still apply. Okay, so this is okay then, because they said that the population, all these students have approximately normally distributed heights. So pulling a sample of size 19, it's like, yeah, that's a pretty small sample, but because the population was normally distributed, I can still talk about the sample means having a distribution that's this student's t distribution. And then we have a sample mean for these 19 to 61 inches, sample standard deviation is 2 inches. And in fact, this is it. Sigma is unknown. The sample was a simple random sample. Population was approximately normal, so it doesn't matter what sample size. I would be using a t-test here. We would be working with a student's t distribution with 18 degrees of freedom. You might recall that from confidence intervals. When you're working with a one population, one sample, the student's t distribution had the sample size minus 1 degrees of freedom. So we'd be talking 18 degrees of freedom here, but this is it. Now let me read the other ones and explain why they're not a scenario where you'd be using a t-test or working with a student's t distribution with so many degrees of freedom. So the second one, a sample mean of 19 miles per gallon and a sample standard deviation of 2 miles per gallon are obtained using a convenient sample of 10 vehicles from a large group of vehicles which have approximately normally distributed fuel consumption rates. Everything's good. The population standard deviation, sigma, is unknown. It's not mentioned here. They said the population is normally distributed or approximately normally distributed, so it doesn't matter that the sample size is 10. The central limit theorem would still apply. But the type of sample. See, it's a convenience sample, right? Remember, convenience sampling is not good. There's a lot of possibility for bias there. So because the sample wasn't taken in such a way that it is a simple random sample, this is not a scenario where I would be applying a t-test or really doing any kind of hypothesis test because the sample is poorly taken. Third one, a sample mean of 84, sample standard deviation of 2, there's x bar and s, are obtained using a simple random sample of size 14 from just some large population. So notice they didn't mention the distribution of the population. It wasn't is not approximately normal. Now for populations whose distributions you don't know, in order to be able to perform a t-test, we need a pretty large sample size. Again, usually the cutoff is 30 or greater. This sample size is too small to assume that we're going to be using a student's t distribution for the sample means. So that's why I would not say I'd be using a t-test here. They didn't mention the population distribution, and if that's the case, the sample size is too small for us to assume that the sample means would have a t distribution. So not that one. That's why. And then finally, you can read through all this fine, but look at the last sentence. The population's standard deviation is 7.6 minutes. Sigma is known here. The population standard deviation is known. And if that's the case, we'd be performing a z-test. We'd be working with the standard normal distribution, not a student's t-distribution. So that's why that's no good either, right? So the only one of these for which we'd be performing a t-test satisfies all the conditions. Sigma's unknown. Your sample is a simple random sample. And if the population is approximately normal, you're cool. If it's some other population, you're pulling a sample size that's large enough, right? Usually 30 or greater. Then you can apply a t-test to make a test, to do a hypothesis test about a single population mean. Okay. And again, they read through again. See here, in order to perform a hypothesis test of a single population mean mu using a student's t-distribution, the data should be a simple random sample that comes from a population that is approximately normally distributed with an unknown population standard deviation. The only option meeting these criteria is in the first answer choice. Okay. So again, please read through your answer explanations, whether you're right or wrong. When you're right, read them just to make sure your reasoning was correct, and when you're wrong, especially read them to make sure you can figure out where you went wrong. So that way, when you see a problem like that again, you might have better luck. You might do better. All right. So hopefully this video helps on this kind of a problem. Now again, we didn't have to find anything. Well, let's see if there's more parts to it. Nope. Okay. So hopefully that helps when you're asked to say, hey, which of these scenarios is and this is another kind of question like that. So I'm not going to do another one. Just what conditions are necessary for you to be able to be working with a student's t-distribution for you to be able to perform this t-test for a population mean. And thank you very much for watching.